So, good evening, everyone. Welcome to the 11th live session for the course Advanced Reinforced Concrete Design offered by NPTEL. I am Arshit Agrawal, a PMRF scholar from the Department of Civil Engineering, IIT Bombay, and I am taking weekly live session for the entire course duration. So in today's session, we'll first have a quick recap of week 10 session that we concluded last week, and then we'll review the week 11 learnings. So week 11 recordings are oriented towards understanding the serviceability criteria of design of a reinforced concrete structure. In this today, we'll start with discussion on deflection in reinforced concrete section, considering both short-term and long-term deflection. In long-term deflection, we'll talk about effect of shrinkage, creep, and temperature, and we'll see how IS code IS 456 design poses limits on deflection for design purpose. After this, we will talk about crack width calculation in reinforced concrete section, and we'll see how, based on the location of on the RC section, crack width can change. And finally, we'll talk about bond between steel and steel reinforcement and concrete, and different factors which can influence the bond stress, how bond failure occurs, and what is the concept of development length and splicing and its design. So today, along with quick theory recap of different segments, I will introduce you with several questions to just challenge your understanding. In total, we'll have around 12 to 13 questions that we'll discuss, some numerical and some theoretical. And at the end, I will make myself available to solve any queries related to the assignment part. So last week we started discussing about the design of eccentrically loaded column. We first saw design of uniaxially loaded short column, for which we understood the PM interaction curve. So this curve has three zones. Compression zone, that is the value of eccentricity till which net concrete will be in compression and compression failure dominates. Then we have balanced eccentricity where both concrete and steel fail together, and beyond this balanced eccentricity we have tension failures that dominate in the cross section. So design of uniaxially loaded column, it depends upon the location of neutral axis and stress acting in the cross section. So when the neutral axis depth is more than the lateral dimension of the column, we say that the net column is in compression, and so the design of column in the design of column, all steel reinforcement and concrete, they contribute to compressive stress. Okay. However, if the neutral axis depth is less than the lateral dimension of the column, then we say column is in both compression and tension. Okay, so net equivalent compression on the cross section will be total compressive force minus total tension force. Okay, now theoretically, designing such eccentrically loaded column is complex because stress distribution is not uniform, and it can be difficult to every time calculate the location of this force and the amount of this force. Okay, so as an alternate, we use SP16 design chart. So here, knowing the grade of steel, effective cover to total depth ratio, and ultimate load and moment factors, we can estimate the percentage reinforcement required for a column to resist the load and moment. So we saw numerical how we can use these SP16 charts for designing a reinforced concrete section. Then we talked about biaxially loaded column, where now there are two PM interaction curve. There is case A and case B. Okay, and there can be infinite cases in between them also, depending upon where the load is situated. Okay, so these two cases, they are present at an angle of 90-degree, which can span multiple cases, all cover all possibilities of eccentricity between it. Okay, for designing such column, we used load contour method as proposed by IS 456, which follows this relationship MUX upon MUX1 to the power alpha n plus MUY upon MUY1 to the power alpha n should be less than or equal to 1. So here MUX and MUY are the moment to be resisted, and MUX1 and MUY1 are the moment capacity of the column in uniaxial direction for that PU load which is acting on the column. And alpha n is the load factor which whose value depends upon the design load to ultimate load. Okay, for this also we saw numerical how we approach the problem. And finally, we discussed about slender column, what are slender column, and why movement is generated due to slender column, and why they fail prematurely compared to short column. We talked about different curvature of bending in slender column and how these curvature change in braced and unbraced column. For braced column, we saw deflection is controlled by member stability effect, while for unbraced column, deflection is dependent upon both member stability effect and lateral drift effect. This lateral drift effect, it is generated due to the lateral displacement of the frame in the unbraced condition. Okay. Now for designing such column, we talked about additional moment capacity method, according to which net moment is the moment acting on the column plus the additional moment generated due to slenderness. And based on clause 39.7.1, we saw how slenderness ratio can be quantified in different direction. For braced frame, to calculate the moment acting on the column, suppose the top and the bottom of the column is subjected to different bending moment, then we saw how we can calculate the net moment acting on the column. Okay. And for unbraced condition, again we saw how net moment is calculated. It is just basically the maximum primary moment. So in braced condition, we take a proportion of both top and bottom moment, while in unbraced condition we just take the maximum primary moment whether it is on top or bottom. Okay. So for this part also we saw one numerical how to approach. Okay, now coming to the week 11 content, if we go back to our first live session, we discussed about different design method of reinforced concrete. Okay, so what are the basis of these design methods? They first to ensure adequate safety, second to ensure adequate serviceability, and third is economy. Okay, so we talked about three design methods. First is working stress method, or we say modular ratio method, in which the design of reinforced concrete is done for service loading condition while the strength of reinforced concrete section is reduced by some factor. Then there is ultimate load method or load factor method, in which we consider different combination of loading that is acting on a reinforced concrete, which is amplified by a certain loading factor without reducing the strength of concrete. And finally, the most commonly used method is the limit state of uh, limit state method. Okay. Now what's common in all these three method? It is the basic need of design. So that is the load acting should always be less than the resistance offered by a RC section. Now, the design philosophy of this limit state of design is more advanced than any other traditional design philosophy. So, if we see in working stress method, the calculation are done for working load, and in ultimate load method, the calculation are done with ultimate load. But in limit state method, ultimate load is taken for safety and working load is taken for serviceability. It is combining both ultimate load and working load. Okay. Now, what do we mean by limit state? So, limit state is basically acceptance limit for safety and serviceability requirement before failure occurs. Okay, so we have two types of limit state of strength, limit state of safety, and limit state of serviceability. So this limit state of strength or limit state of safety, it is associated with the protecting the failure of structure, and when the worst possible load combination is taken into consideration. And limit state of serviceability is associated with satisfactory performance of a structure during working load condition. Okay, so this is ultimate load. Okay, worst combination that we are taking for limit state of strength, or we can say limit state of safety. Okay. And when we talk about serviceability, we don't take worst possible loading condition because that won't occur always. So we just take working load, working condition or service condition. Okay, so in that, my structure should perform satisfactorily. Okay, so that is taken into account by limit state of serviceability. Now, why do we need this limit state of serviceability? So, when a reinforced concrete section it is designed for limit state of strength, we consider worst possible loading condition. Okay. Now to adopt for this ultimate loading condition, designer generally they opt for higher grade of concrete and steel. And what happens? This eventually leads to a final reinforced concrete design which comprises of a thinner cross section and higher stress level, since we are opting for higher grades of concrete and steel. Now, Due to this, what can happen? It can lead to high deflections, cracking, and vibrations in my concrete under normal loading condition. Okay, if there are such cases of deflections and cracking in normal loading condition, it can raise concerns regarding comfort of occupants and aesthetic appearance of the structure. Okay, so remove such safety concerns under serviceable condition, we incorporate the limit state of serviceability criteria. Okay. Now, as per IS 456 design method, serviceability limit state is defined as the state beyond which a structural system loses its serviceability and it cannot be operational under actual service load that the structure is subjected to. So basically, we have designed for ultimate state, but under service loading condition there are certain criteria that the structure needs to fulfill. If it is not fulfilling those criteria, then we say that the structure is not designed adequately and it needs to be redesigned. Okay, so code checks on serviceability. It checks based on two conditions. First is the total deflection in the RC section, which can come in both short term and long term, and second is the crack width in the reinforced concrete section under different structural conditions. Okay, so we'll see each of these criteria, deflection and cracking, one by one. Okay, so let's first start with the deflection part. Okay, why do we need to check for deflection? Okay, so to answer this, we need to understand what will happen if there is excessive deflection in a reinforced concrete section. So suppose this is my beam and it has undergone excessive deflection like this. Okay, due to a load acting on it. So what is the problem with such deflection? So there are different problems that can occur due to excessive deflection. Okay, the first is visual appearance. So if this deflection is more than the span length of the beam divided by 250, then it will it won't make the beam look good visually. Okay, so that visual appearance can be a problem. Then due to such deflection there can be damage to non-structural elements like cracking in partition walls or malfunctioning of doors and window that can occur due to such large deflection. Then there can be disruption in functioning of sensitive machinery or equipments, or there can be ponding of rainwater on the roof. So suppose the slab at the roof, it undergoes such deflection, so what will happen? The water will start to accumulate over the roof. Okay, so that can result in ponding of rainwater on roof. That can be one problem. And there can be damage to structural element due to such large deflection also, which is possible. Okay, so excessive deflection is a problem in the reinforced concrete condition, and this all thing we are talking in service loading condition, not even in ultimate load condition. Now, checking for deflection in reinforced concrete is not as easy as it is said. Okay, there are several challenges that are associated with deflection check. What are these challenges? So, first of all, there is uncertainty in predicting the flexural rigidity of a reinforced concrete section. Okay, this flexural rigidity of a section can vary due to several reasons. Due to varying tensile cracking in concrete. So, when we talk about a reinforced concrete beam, it is not cracking uniformly throughout. Okay, there is cracking some in the mid span, there is cracking at the edges. Okay, so the tensile cracking in concrete varies, the degree of cracking varies along the section. Okay, so this flexural rigidity of concrete will also vary around the section. There can be varying amount of flexural reinforcement that we know. Okay, here we provide compression reinforcement, here we are providing tension reinforcement. Okay, there can be varying modulus of elasticity of concrete. Okay, for beams we are using different grade of concrete, for columns we may use different grade of concrete, so that can lead to difference in flexural rigidity of a reinforced concrete structure. And varying modulus of rupture of concrete. So we know modulus of rupture of concrete is directly proportional to the square root of compressive strength of concrete. So if compressive strength of concrete is varying, then the modulus of rupture of concrete will also vary. Okay, now, apart from this, there can be uncertainties related to the time dependent and environmental effect, like influence of creep and shrinkage, which can make deflection check a problem, not a very easy task. There can be flexural, inelastic flexural behavior of member that is occurring, or there can be invariant, inherent high variability in measured deflection, okay, if it is not performed control it, if it is not controlled properly in field condition, okay, and even in laboratory condition, okay. So there can be several reasons which can pose challenge in checking the deflection. A small illustration of how complex deflection behavior in reinforced concrete is can be seen through this example. So, suppose we have a reinforced concrete beam which is subjected to a uniformly distributed load. So, as loading will increase, what will happen? The end of the beam, it will be, since it is subjected to a higher moment, it will show some crack initially in the compression zone, okay. Now further we will start to see crack in the mid span also in tension zone. Why? Because concrete is brittle and has low tensile capacity that we generally ignore in design, so we'll see some cracking in the tension zone also. Now, so we are, as we are increasing the load, this was the point where we saw end of the beam cracking, and then we reach the point B where cracking in the midspan starts to happen. Now further, as the load increases, the bending moment will increase, okay. So if we have a under reinforced design, we'll see that the stress in steel will also increase slowly, and hence the strain in steel will also increase. So as the strain in steel will increase, what will happen? The reinforced concrete will start to deflect a little even under service loading condition. Why? Because we have a under reinforced section. So in under reinforced section, my steel has reached the yielding. Okay. So as I'm increasing the stress, the strain in steel is increasing. So curvature will slowly increase in the steel also. Okay. So that's why the midland deflection, it may increase further. Okay. Now if we keep this service load constant, then the deflection will further grow at this load also. Why? Because of creep effect, okay. However, if we increase the load beyond this point, then what will happen? The steel will yield, and if it can't take any amount of higher stress, then the deflection will continuously increase, and then the loading capacity will decrease and the deflection will continue to increase. So this is how load versus deflection behavior in a reinforced concrete can change based on the amount of loading that is there on the section. So as loading will increase, the cracking will grow, okay, and there will be deflection in the beam. Now we know that a cracked beam starts to lose strength as the amount of cracking increases. So if we plot this flexural rigidity of concrete versus the moment that is acting on the concrete, so beyond a certain moment which is known as cracking moment, okay, we'll see that the praxial rigidity of a reinforced concrete beam, it will continuously decrease with increasing moment, and this decrease, it tends to reach saturation when the moment increases beyond the ultimate moment and the steel reinforcement starts to yield, okay. So this limit, therefore it is known as cracked section. So this point B, where the moment has reached the point till which there is yielding of steel, we say that this moment, this section is known as cracked section, and the flexural rigidity value, the EI value corresponding to this, is known as cracked EI, okay. So if we plot the moment versus curvature, okay, how the moment versus curvature is changing with increasing moment. So we have two well-defined point. First is point A, where which is the limit of this uncracked EI. Okay, my moment is just reached the cracking moment. Okay, so till this moment, when the moment is less than this cracked moment, we say that the curvature of this moment versus the slope of this moment versus curvature will be E times I. So E is the modulus of elasticity of concrete, and I is the uh, uh, moment of inertia of concrete. So IGR, we say E times IGR, gross moment of inertia of concrete. Now, second well-defined point that we have is B, corresponding to cracked EI, where the slope of moment curvature will now be E times I CR. Okay, so cracked moment of inertia of concrete. Okay, now for any moment between these 2 points, what will happen? The slope will continuously decrease. Why? Because EI continuously decreases. So moment curvature and deflection, moment will increase and deflection will continuously increase like this. Okay, so this is the representation of moment versus curvature of a reinforced concrete beam which is subjected to a certain amount of bending, and how with increasing bending the curvature is increasing. So two well defined points we have. Okay, now if we take a clearer representation of this curve, okay, so what is happening, we have two cases. Case A, where m is less than mcr, so for that we can write curvature is m upon e times I gross. Okay, however, when m is greater than mcr, okay, so this is my mcr and suppose this is my m, okay, somewhere between the ultimate moment and the crack moment. So we write that, we say that E value, that the modulus of elasticity of concrete doesn't change much, but and continuously decreases. So curvature will be nothing but m upon E times I effective. Okay, so we are not taking gross moment of inertia, we are taking some effective moment of inertia. And this effective moment will be less than gross moment and more than the cracked moment. Okay, because at cracking, there will be saturation. So effective moment is somewhere in between this point that we are considering. Okay, now how to calculate this effective moment? So at point A, we know m is equal to mcr and ei is equal to ei gross. And at point C, we know m is equal to ultimate moment, and ei at this point it decreases to 85 percentage. Okay, so ei is like 85% of cracked section ei. Okay, so at this point, I effective it is 0.85 ICR. Okay, so why this 0.85? It is just a conservative design factor that is taken into consideration. So for any point B between MUR and MCR, um, so moment will be like M will be greater than MCR and M is less than MUR. So how to calculate E effective, EI effective for this? So by bilinear approximation, suppose from point O to point C I go, I know the slope of the line is 0.885 times ICR. Now the same thing we will assume for trilinear approximation also. So we will assume that the slope of this line is equal to this line. So we can say EI effective. So we know the slope of this line now. Okay, this slope we know. We know the difference in moment. So moment that we have applied is M and cracking moment is MCR that we can calculate. And we know deflection at moment M we are taking as phi, and at cracking moment deflection is phi CR. So M minus MCR upon phi minus phi CR will be nothing but the slope theta, which is equal to 0.85 times EICR. Okay, so if we'll simplify this, we'll get EI effective as m upon delta m upon phi, which is equal to this relationship. Okay, so this relationship we can just simplify from this equation of perpendicular upon base is equal to the angle theta. Okay, now how to get this cracked deflection, cracked curvature, and cracked movement? So for that we can use flexure theory. So from flexure theory we know my by I is equal to the flexural stress. Okay, so this m I can write as sigma times I upon y, and so we have written sigma as FCR, cracked stress in concrete, times I gross upon YT, and this cracked moment stress of concrete, it is equal to zero point 0.7 times under root of FCK. So we can get the value of MCR, and dividing MCR by E times I gross, I will get the value of phi CR. Okay, so these value we have known. So if we know these value and we know how much moment we have applied, we can calculate the value of EI effective. But since we know that E is not changing much, so we can simplify this relationship into I effective also. So we can write I effective as I effective is equal to ICR upon 1.2 minus MCR upon M times neta. And here neta is this factor 1.2 minus ICR upon IGR. So this relationship that we saw here, they simplified into this. Okay, since E is not changing much. Now what IS code have done, they have tried to relate this gross moment of inertia and cracked moment of inertia with neutral axis depth, and they came up with this relationship for neta. So neta is equal to 1 by z times 1 minus x by d times bw by b. So this relationship they derived so that we can relate gross moment of inertia and cracked cracked moment of inertia. Okay, so Z we know lever arm distance, D is the effective depth, X is the neutral axis, which can be computed by equating the compression and tension moment of inertia. BW is the breadth of web, and B is the breadth of compression phase. Okay, so using this relationship we can calculate the value of neta. So knowing the cross section of a reinforced concrete beam, the reinforcement detailing and the moment acting on the beam, we can determine the I effective value, which we will use to compute the short term deflection in the reinforced concrete beam due to loading condition. Okay, so this was the basis of design. Okay, so instead of using gross moment of inertia, generally for crack, for deflection calculation we need effective moment of inertia. Why? Because when moment is more than the cracking moment, there is drop in the moment of inertia value. So I gross won't give us a correct value. That's why we are going with I effective. Okay, so just based on this simple understanding about short-term deflection, try to answer these questions. Later on, we'll see one numerical also. Right now, I'm just giving you some theoretical questions to think about. And in the meantime, if you have any doubt with this section, you can ask. Any doubt in the discussion till now, you can type in the chat box, else try to answer these questions. So first question is, in limit state of serviceability, the short-term deflection of an RC beam under service load primarily depends upon which factor? So when we are talking about short-term deflection, which factor contributes? Yes, Khushbu, you can ask. If you are unable to unmute and speak, you can type in the chat box also. In the meantime, can anyone tell me the answer for question number one? Yes, the correct answer is C. Okay, so we have just seen in the theoretical discussion right now that it is the flexural stiffness of the section which is contributing to the decrease in the. So, as cracking increases in concrete, the flexural stiffness of the section decreases, which leads to deflection, more deflection in the section. Okay, so that is the factor that is contributing in short-term deflection. In long-term deflection, we'll see effect of shrinkage and creep in concrete. The second question, the effective moment of inertia, I effective, of a cracked reinforced concrete section is evaluated using Bresson's equation. The equation ensures, so the relationship that we saw right now, I gross, I cracked, and I effective, this is Bresson's equation. So it blends both cracked and uncracked stiffness. Okay, so that blending of cracked and uncracked stiffness was derived by a scientist named Bresson. So that's why we say it as Bresson's equation, this equations that you see here. Okay, so what will be the correct answer for this? What will be the range of I effective? Yes, the correct answer will be B. So we saw in the diagram that just when the cracking begins, we have uncracked EI. Also, okay, so at point A, we have EI gross, okay, and at point C we have EI cracked, okay, and whatever deflection is occurring at any moment between these 2 points, that I value that we are calculating, I effective, will be less than a gross effective. It will be more than cracked moment of inertia. Okay. Question number three. In serviceability limit state, excessive deflection is undesirable mainly because, why excessive deflection is undesirable? So just based on the theory part that we discussed, and the answer should be simple.
பாத்தீங்களா? அது மாதிரி மண்டல போயிட்டு சொல்லுவாங்க.
I guess
நம்ம
you have
வளர்த்து
unmuted
ஆறு
mistakenly.
மண்டல போய்
Do you have any doubt?
அது தெருக்கள் என்ன அது மண்டல போய் அப்படின்னா
Okay, can anyone tell me the answer for question number C? Question number 3. Okay, so for third question, the correct answer will be C. Okay, we saw when there is excessive deflection, it leads to psychological unacceptability of the structure and functional issues. Okay, so that's why we don't want excessive deflection in a reinforced concrete section because it doesn't appear well. Okay, and it can hamper the working condition of non-structural as well as structural elements also. Now try to answer these three more questions related to short-term deflection. In short-term deflection analysis, the modular ratio ES by EC is introduced mainly to. So when we calculate the depth of neutral axis in the NPTEL session, you may have seen that we calculate modular ratio. Why we are calculating modular ratio? Can anyone tell me the answer? You can unmute and speak also if you know the option, which option is correct. Yes, to transform the steel area into equivalent concrete area. Okay, so we calculate modular ratio so that we can transform the steel area into concrete area, and then we equate the moment of inertia of steel and moment of inertia of concrete below and above neutral axis to calculate the depth of neutral axis. Okay, so that is this is known as transformed section analysis that we use to calculate the moment of inertia and stiffness. Okay. For two beams having identical cross section and reinforcement ratio, the one with higher span length will show. So we have two beams, they have identical cross section. So B and D are same and the reinforcement ratio is also the same, but the length is different. The span length is different in the beams. So what will be the correct answer regarding short term deflection? Which will show more deflection? Okay, yes, the correct answer is B. So if you see deflection, when we talk about point load, deflection is directly proportional to the cube of the span length. And in uniformly distributed load, deflection is directly proportional to the uh, span length to the power 4. So even though we have identical cross section and reinforcement ratio, the EI value of the sections will remain the same. But the longer span beam, it will go undergo larger deflection, so that's why higher deflection because of span, since the span term dominates. Okay, so that's the answer will be B. Which parameter most directly control the shape of load deflection curve of a reinforced concrete beam in short term range after cracking? Okay, so the slope that we calculated, which we assumed at 0.85 times ICR, which parameter is most directly controlling that slope? Okay, so the correct answer for this question is A. Why? Because when we talk about moment greater than cracking moment, then we need to see how stiff is my reinforced concrete beam to resist that cracking. And that's why we talk about tension stiffening effect of concrete between crack. So suppose in a reinforced concrete beam, I have reinforcement in the compression side also and the tension side also. So what happens due to reinforcement on the compression side, the deflection is lower compared to uh, beam where there is no compression reinforcement. By because there will be a stiffening effect that will be generated under the loading. So that's why you say tension stiffening effect of concrete between cracks. It also, it is the, it is this parameter most directly control the slope. Okay, so that's why we have taken that factor as 0.85 times ICR right now. Okay, that was just for safety consideration. Okay. So this was about short-term deflection. Now we'll see one numerical, but just a little bit later. First, after talking about long-term deflection also, then we'll see numerical combining both. Okay. So till now we have talked about deflection due to loading. Now in practical conditions there are more than one form of deflection which can occur in a reinforced concrete beam, and this can account for 2 to 3 times a higher magnitude compared to the deflection just due to loading. Okay, and these deflections are known as long term deflection. Okay, so in long term deflection in reinforced concrete section, it increases with time mainly due to three effects: shrinkage, creep, and temperature. So, first, we will talk about differential shrinkage. So, differential shrinkage, it causes differential strain in a reinforced concrete section, which results in curvature. Okay, so if we just touch up upon what is shrinkage. So shrinkage, we know, is it a time dependent and load independent phenomena, and it occurs due to volume reduction of concrete due to hydration and drying. Okay, now why deflection occurs due to shrinkage? So uh, if the shrinkage is uniform and reinforcement is symmetric in a reinforced concrete section, when then we say that the member shortens uniformly and there is no curvature. However, in real reinforced concrete beam and slab, the reinforcements are unsymmetric. There is generally more bottom reinforcement than top reinforcement, and there is a through that gradient also which is present. Since the top part, it dries more compared to the bottom part. So such reasons, they result in differential restraints in the reinforced concrete beam, which produces curvature and deflection in the reinforced concrete section. Okay, so if we have uniform cross section, uniform reinforcement of steel, uniform distribution of steel reinforcement, and uniform drying of concrete, then we won't see any deflection due to shrinkage. It is just the variation in the reinforcement distribution and the variation in the temperature gradient or exposure of a reinforced concrete section that brings in deflection due to shrinkage. Now we can have a quick visualization of shrinkage here. Like if you see a simply supported reinforced concrete beam subjected to uniformly distributed load, we have top reinforcement as ASC and we have bottom reinforcement as AST. So if my AST, the bottom reinforcement is more than ASC, then what will happen? The top part, it will shrink less compared to the top part, it will shrink more compared to the bottom part. Okay, so we'll see a deflection profile, it will come like this. So the curvature at the top we can write as the difference in the strain produced at the top and the bottom divided by the effective depth. So this is the curvature we can write: deflection at the bottom minus deflection at the top divided by the effective depth of the section. Similarly, if we apply the same concept for a cantilever beam also, we can see there can be more deflection at the top while there is less deflection at the bottom. So we can write the curvature as difference between the strain at top and bottom divided by the effective depth. Now this is the relationship that we know. The curvature due to shrinkage is the difference in the strain at top and bottom divided by the effective depth. Now, if we modify this relation a bit, we can write curvature at the top as the ratio of ultimate shrinkage strain in concrete, which is equal to epsilon Cs divided by the total depth of the section times a factor K4. Okay. Now, this factor K4, it depends upon the relative ratio between the top and the bottom reinforcement. Okay, so if the ratio, if the top minus the bottom reinforcement ratio is less than 1 and greater than 0.25, then K4 value is calculated using this formula. And if this ratio difference between top and bottom reinforcement percentage, it is more than or equal to 1, then we calculate K4 using this formula. Okay, if this is equal to 1, if both top reinforcement and bottom reinforcement they are equal, then we'll see there will be no strain that will appear due to shrinkage. So this curvature due to shrinkage will become zero. Okay, so that's why you can see in both the formula pt minus pc, if pt is equal to pc, k4 will be equal to zero, so strain will become equal to zero. It is just because of the difference in the reinforcement distribution that shrinkage strain appear. Okay, that deflection appears due to shrinkage. Now, how to relate this curvature to deflection? So right now we have calculated curvature. How this curvature is related to deflection? I guess someone has unmuted. Okay, so the relationship between deflection and curvature for a set, any set of boundary condition, it can be established by standard methods of structural analysis, which are based on conjugate beam theory or moment area method. Like few examples, it was given you in this session, like 0.25 times the curvature, the deflection curvature times L square, it is for simply supported beam, then 0.5 times curvature times L square, it is for cantilever beam, and for fixed beam and propped cantilever also we had the relationship. So using these relationship we will get the deflection in a reinforced concrete beam due to shrinkage. So we can simply write this equation, the entire concept, as deflection due to shrinkage is some factor K3 times K4 times the strain in concrete times L square by D. So this K4 factor, it will depend upon the, it will vary between 0 and 1 depending on the relative magnitude of tension and compression reinforcement, and this K3 factor will depend upon the end condition. So it can vary between 0.063 to zero point 0.5 depending upon the boundary condition. Okay, so this K3 and K4 will get based on the reinforcement RC section design and boundary condition. Epsilon Cs, we know it is 0.0003 ultimate shrinkage strain in concrete, and L square by D, again these are dimensional properties of concrete. Okay, so using this, we can calculate deflection due to shrinkage. After shrinkage, another factor which contributes to long-term deflection is creep under sustained loading. So quickly reviewing what is creep. So creep is a time-dependent and stress-dependent effect. Okay, so shrinkage was time-dependent and load-independent effect. Here we have time-dependent and stress, or we can say load-dependent effect. Okay, so and it results from sustained compression of a reinforced concrete section in loading, which results in uh, additional strain generation in concrete, which results in deflection. Now, why deflection is occurring due to creep? Okay, so when they sustained sagging moment on a reinforced concrete, the top part of the reinforced concrete remains in compression, and due to this shrinkage, the creep increases the compressive strain and it amplifies the curvature and the mid-span deflection. So suppose I have a reinforced concrete beam, it is continuously subjected to some load P. So what will happen? Slowly, the curvature of this beam will increase. Okay, so due to this, the deflection due to this load, though this load is under serviceable condition, it will increase the strain in the compressive part of concrete, which will lead to increasing the curvature and the deflection at the midspan. Okay, we know that steel does not creep, so the entire stress it shifts to steel, and the neutral axis it tends to move downward. Okay. Now, apart from creep, one final factor which accounts for long-term deflection is the temperature effect. So in a statistically indeterminate frame, temperature effects can also come into account. Okay, so under uniform temperature change, when there is free expansion, there is no curvature. However, if the ends are restrained in a section like a continuous frame, it induces secondary movement and deflection in the frame due to temperature gradient. However, from design point of view, we generally ignore the effect of temperature gradient because its magnitude is comparatively very small compared to creep and shrinkage. So whenever we are talking about design, we just talk about deflection due to creep and deflection due to shrinkage. Okay, so if we see how creep causes deflection in a reinforced concrete section, so suppose we have a reinforced concrete section with bottom reinforcement. So due to creep, what happens? There is increase in concrete strain from epsilon I to epsilon I plus epsilon Cp. Now, due to this, the neutral axis depth it's moved downward, and the strain in steel will also increase. Okay, at the bottom, and as a result the curvature which is represented by epsilon times y, it also increases from phi I to phi I plus phi cp. Okay, so this is the effect of creep. Okay, the strain is increasing in the concrete, which due to which the neutral axis depth is lowering, and this is also increasing the strain in the steel, and the net curvature of the section is increasing. If the net curvature of the section will increase, the deflection will also increase. So if we see understand this from stress versus strain distribution, for a particular sigma I, initially the moment of modulus of elasticity of concrete is represented by EC, and the strain corresponding is epsilon I. Now if this load is maintained under sustained loading, what will happen? The strain will increase from epsilon I to epsilon I plus Cp. So the modulus of elasticity of concrete it will reduce, okay, from EC to ECE, and by what factor? By a factor of 1 plus theta. Here theta is known as the creep coefficient. Okay, so this theta is the creep coefficient due to which the moment modulus of elasticity of concrete has decreased under sustained loading condition. So we write EC is as EC upon 1 plus theta. Now, how to get the value of theta? So, as per clause 6.2.5.1 of IS 456, this value of theta depends upon the age of concrete under loading. So, with this value of theta, we can take as 2.2 for ages of loading equal to 7 days, 1.6 for ages of loading for 20 days, and 1.1 for an age of loading of 1 year. Okay. Now, how to estimate deflection due to creep? So this was just the change in the modulus of elasticity that we checked. How to estimate deflection? So for this, we need to calculate deflection under different conditions. So we'll calculate deflection due to characteristic live load plus dev load, and that will be represented by delta D plus L. Then we'll calculate deflection due to permanent dead load, that will be represented by delta I. We'll calculate deflection due to permanent load plus creep considering effect, where EC will be changed to ECE. Okay, and we'll calculate the deflection, and finally difference between these two, delta I and delta I plus delta I plus Cp, will be our creep deflection. Okay, so with the numerical we understand this entire process, how the calculation is done. Okay, so we have seen in long term deflection two effects. Okay, effect of shrinkage and effect of creep, and in short term deflection the effect is due to the loading. Okay, so let's see a numerical here where we'll estimate all different kinds of deflection that we have talked about. So why we are seeing everything together? Because in exam it won't come like you need to calculate all types of deflection in one go. In a single question you may need to calculate only one type of deflection. However, if you'll see all types of deflection, it will provide you clarity if needed. If you need to compare two different deflections together, then also it can do. So it will be a good practice for exam. Okay, so this is the question that we'll talk about. So I will pause myself for a minute, I will mute myself for a minute, and I will let you read the question thoroughly, and then we'll see how to solve this question. Okay. In the meantime, if you have any doubt regarding creep deflection and shrinkage deflection, that you can ask. Okay. So just think about this question, how we can approach this question. Ravinder, I guess you muted. Ravinder, I guess you unmuted yourself mistakenly. If you had any doubt and you wanted to ask, you can unmute again and speak. Okay, so can anyone tell me how we'll approach this question? So we know the permanent dead load, we know the live load, and we know how much percentage of light load is sustained for longer period. We know the width of the section, we know the overall depth and effective depth, and we know the reinforcement. So we have bottom reinforcement, then there is no top reinforcement. We know the grade of concrete, modulus of elasticity of concrete, and modulus of rupture. Okay, for cracking moment. And we know the grade of steel and modulus of elasticity of steel. Okay, so how we can calculate short term and long term deflection? Can anyone tell me just the procedure, how you will approach this question? Anyone wants to volunteer? Just tell me whatever you understood from the discussion till now. How deflection is calculated. Anyone wants to volunteer and then speak? Or else, or should we go forward with the saying the solution to this question? Oof. Okay, so let's see how we'll approach. So what we'll do in this question, first we need to calculate the moments and the stiffness of the section. Okay, what is the moment, cracked moment of inertia? That is my first point that I need to calculate. Okay, gross moment of inertia and cracked moment of inertia. Once I know these two values, I will calculate the neutral axis depth, I will calculate the lever arm distance, and I will calculate the effective moment of inertia of the section. Okay, once we know the effective moment of inertia, we can calculate the deflection due to dead load plus live load. Okay, so that is 14 plus 10, 24 kilonewton per meter. Okay, so deflection will calculate. Okay, so that will be deflection due to live load plus dead load. Now for shrinkage, we'll calculate the K4 value and then we'll calculate deflection due to shrinkage. So we know it is a simply supported beam. Okay, so K3 value will know, K4 value will calculate, and we'll get the deflection. And for creep, we know the creep coefficient. Uh, we know it is given. Okay, for 28 days, assuming 28 days, it is given to us. So we'll know the creep coefficient. So we'll calculate the modulus of elasticity of concrete. Okay. that will be equal to epsilon modulus velocity of concrete initially divided by 1 plus theta. Theta is 1.6. Okay, then we'll calculate, we know the instantaneous deflection we can calculate, okay, based on the permanent dead load plus superimposed creep load, which is 40% of 10, which is 4. So 4 plus 14 will give me 18 kilonewton per meter. So with that we can calculate the delta, and due to creeping we change the EC value to ECE and we'll calculate the delta again, and the difference between the two will give me the creep deflection. Once we know the creep deflection, we can calculate the long term deflection, okay, and we'll calculate the amplification. Okay, so this is the approach. Okay, so let's see part by part. So first of all we will check the section moments and stiffness value. So gross moment of inertia, we know it is given by BD cube by 12. B is equal to 300, D is equal to 600 cube by 12. Okay, so 300 into 600 cube by 12, it will give me a value of 5.4 into 10 to the power 9 mm to the power 4. Okay, so this is my gross moment of inertia. YT value, it is nothing but total depth divided by 2. So it will be 600 divided by 2, which will be equal to 300 mm. Okay, so modulus of rupture of concrete, we know it is zero point 0.7 under root of FCK. So this we can calculate as zero point 0.7 under root of 30. So this will come out to be 3.834 MPa. Then knowing all these value, we can calculate the cracked moment of inertia, which we saw based on flexure theory. It is nothing but FCR times Ig upon Yt. So we know all the three values. When we'll substitute all these three values, we'll get cracked moment of inertia as 69 kilonewton meter. And what is the actual moment which is acting on the section? It is WL square by 8. So W is nothing but 14 plus 10, dead load plus live load, into L square. L is 7 meters. So 7 to 7 square by 8. Okay, so this is 147 kilonewton meter. So whatever moment is right now acting on the concrete, it is more than the cracked moment of concrete. So that's why we need to consider I effective. If this moment which is acting on concrete would be less than 69 kilonewton meter, then I effective will be I gross only. Okay, since it is more than the the cracking moment of concrete, then we are using I effective. Now modular ratio is the ratio of modulus of elasticity of steel upon modulus of elasticity of concrete. So modulus of elasticity of steel, we know it is 200 GPa, and modulus of elasticity of concrete is given by 5000 under root FCK. So when you do the calculation, it will be 200 GPa. Okay, 200 GPM converting into MPa, so 200 into 1000 divided by 500 under root FCK. So upon doing the calculation, you will get modular ratio is 7.3. Okay. Now we know the modular ratio, so we'll calculate the neutral axis depth from transformed section analysis. So bx square by 2, it is the moment of inertia of concrete segment, and n into as into dA minus x is the moment of inertia of steel section. So n is this modular ratio. So we have transformed steel into concrete. Okay, so when you substitute the value, it will be 300 into x square by 2 equal to 7.3 into as 1963 into d. So that is 460 minus x. Okay, so d is given to us. It is 540 minus x. Okay, so when you will do the calculation, you will get value of neutral axis depth x will be equal to 184.36 mm. Okay, now we know the value of neutral axis depth, so we can calculate the cracked inertia. So it is nothing but this modular moment of inertia of the area movement of concrete times the distance of its center of moment, which is 2x by 3, plus the area of moment of transform steel times its distance from the neutral axis, which is d minus x. So that's why it for the formula comes out to be bx cubed by 3 plus n into as into d minus x square. Okay, so when you will substitute all the values that we have calculated, okay, so x we know, b we know, as we know, and n we know, and d we know. So we'll get a cracked moment of inertia as 2.44 into 10 to the power 9 mm to the power 4. Okay, so this is my cracked moment of inertia. Okay, lever arm distance now we can calculate, it is d minus x by 3. So 540 minus 184.36 by 3. So it will come out to be 478.55 mm. Okay, and we can calculate the factor neta that we saw we require for I effective. So neta will be z by d. So z is 478.55 divided by 540 whole into 1 minus x by d. So 1 minus x is 184.36 divided by 540 whole into 300 by 300, because the web width and the total width of the section is the same. Okay, so this value will come out to be 0.584. Now we know value of neta, we know mcr, we know the moment that is actually acting, and we know the cracked moment of inertia, so we can calculate the effective moment of inertia. So and you will substitute all these value of I mcr, m icr, and neta in this formula. Okay, you will get I effective as 2.635 into 10 to the power 9 mm to the power 4. Okay, so this is how we approach the problem. Okay, how we calculate I effective. So first, gross moment of inertia, then we calculated the cracking moment of inertia. We checked whether the actual moment which is acting is more than cracking moment or not. Then we calculate the depth of neutral axis by equating the area moment of concrete and steel. Then we calculated the cracked inertia by multiplying the area movement with the distance of the center of section from the neutral axis. Okay, we got the cracked moment of inertia. We calculated the lever arm distance. We calculated the value of neta, and then we calculated I effective. I effective will come out to be this. Okay, so this was the first part. Now from I effective, how we can calculate the total deflection. So for a simply supported beam under uniformly distributed load, the deflection is given as wl to the power 4 upon 384 ei. So we know 5 w is 24 times L to the power 4. So 7 meter I will convert into mm. So 7000 to the power 4 divided by 384 EI. So 384 into E, so that is 5000 under root FCK times I effective. So that we calculate is 2.635 into 10 to the power 9. Okay, so upon substituting all the values, you will get instantaneous deflection due to dead load plus live load as approximately equal to 10.39 mm. Okay, so this is my instantaneous mid-span deflection. Now what is the deflection due to shrinkage? So first you need to calculate the percentage tensile reinforcement, which is nothing but 100 times AST upon BD. AST we know, it is given to us in the question. So 100 into 1963 divided by 300 into 540. Okay, so this will give me a value of 1.212 percentage, and percentage compression reinforcement, it is equal to 0. No compression reinforcement is provided, so pt minus pc will be 1.212. Now for this value, since pt minus pc is greater than 1, then we need to use the second formula, okay, that we saw in the shrinkage slide. Okay, so here this second formula I will use. Okay, so if I just copy this formula here. Okay, so it will be 0.65 times pt minus pc upon under root of pt. So pt minus pc, it is given to us is 1.212 times under root of 1.212. So this will come out to be equal to 0.716, which is less than or equal to 1. So we k4 value will use as 0.716. So deflection due to shrinkage, then we can write as K3. K3 factor will be equal to 1.125 for simply supported beam. K4 is 0.716. Then compression strain in concrete, it is 0.0003 L square by D. So 7,000 into 7,000 divided by D. So which is 600. Okay. So upon doing this calculation, you will get delta SH will be equal to 2.193 mm. Okay, so this is how we calculate the shrinkage deflection, by first calculating the difference between the tension and the compression reinforcement, then calculating K4 factor. K3 factor will know from the load end support. So we have simply supported beam. So that's why I have taken 0.125 as the factor, and then we'll calculate delta SH. Now, due to creep coefficient, we know it is 1.6 for 28 days loading. So EC is nothing but EC upon 1 plus delta. EC is 5000 under root of FCK divided by 1 plus theta. So 1 plus theta is 1 plus 1.6. Okay, so this value will come out to be 10533 MPa. Okay, now instantaneous deflection due to under sustained loading. So what will be my load that I will consider? It will be 14 plus 40% of live load that is sustained for longer period. So 14 plus 4, which will be equal to 18 kilonewton per meter. Okay, so for this load, we will calculate the deflection, instantaneous deflection, where my moment of modulus of elasticity of concrete will be EC. So this deflection, when you will substitute the value, it will come out to be 7.795 mm. And what will be if creep effect? So in creep effect, we'll just substitute EC with ECE, because modulus of elasticity of concrete, it will decrease under sustained loading conditions. So that's why EC will change to EC. So you will get delta I plus CP. When you will substitute all the values, it will be around 20.275 mm. So what we can write, the deflection due to creep will be 20.275 minus 7.795. So this will be equal to 12.48 mm. So this is the deflection due to creep. Okay, this was the deflection due to shrinkage. Okay, so this is how we calculate deflection due to different conditions: due to instantaneous deflection due to load, if deflection due to shrinkage, and deflection due to sustained loading condition. Now the next part was of the question was calculating the total deflection when the occasional live load is also present. So what will be the total deflection? It will be deflection due to creep plus deflection due to shrinkage plus deflection due to instantaneous loading conditions. So instantaneous load, we saw it is 6 kilonewton per meter. Okay, so in the question we saw 40% of the sustained load is remained. Okay, so 60% is instantaneous and 40% will go for a longer period. So for that 60% instantaneous load, what is the deflection? That will also come into the long term deflection. Okay, so that deflection you can calculate by just assuming 6 kilonewton per meter load, and when you will calculate this deflection, it will come out to be 2.599 mm. So total deflection will be 20.275 due to creep, 2.193 due to shrinkage, and 2.599 due to this instantaneous load, live load. Okay, so that will be 20.057 25.067 mm. So this is total long term deflection. Now if we check the ratio, what is the long term deflection to the instantaneous deflection? So it will be 20.067 divided by the instantaneous deflection that we got was 10.39. So 10.39. So this ratio, it will come out to be 2.412. So you can see how much amplification and deflection it happens under long term loading condition. Okay, so that's why we need to we check for creep and shrinkage effect, so that we can see actually the deflection that occurs in a reinforced concrete section, it is far greater than the deflection that is initially there. Okay, and this is how we approach the problem. So in this, there are multiple parts that we covered. We calculated the stiffness also, we calculated the deflection due to instantaneous loading, due to shrinkage, due to creep, due to occasional loads, and the ratio. So any part from this can come in exams or in assignment. Okay, any doubt with this question? Is everyone clear with the problem? How we approach the question? Any doubt? Okay, so let's go ahead. Now, what IS code says about deflection. So, if we look at clause 23.2 of IS 456, the total deflection due to dead load plus live load plus long term deflection, code said it should be less than L by 250. So, L is the clear span of the beam. Okay, so that should be the total deflection should be less than L upon 250. Okay, and deflection due to just live load plus long term deflection should be less than L by 350 or 20 whichever is less. Okay, and when we say long term deflection, we are including the deflection due to shrinkage, creep, and temperature. Generally, this temperature effect we nullify because it is very small compared to creep and shrinkage. Now, what if this limit is not what if these limits are exceeded? So in such cases, we need to check if the excess can be contained by providing some other means or not. Okay, so excess deflection can be controlled by some other means or not. What are different means? So we need to check if the excess deflection can be contained by providing a camper. Now, what is a camper? So basically, camper is an upward deflection that is created in a pre-stressed concrete by applying certain pre-stressing force in the steel strands. Suppose this is my reinforced concrete beam. It is loaded with pre-stressed rebars. So in this rebar, we apply some pre-stressing load such that this beam deflects upward. Okay, then this beam deflects upward initially, then after loading the net deflection downwards, it will reduce. Okay, so this is known as camper, the initial upward deflection that we provide in a beam due to pre-stressing. Okay, so that is known as camper. And this is done to limit the overall deflection in the meat span after at under acceptable limits. Okay, so this delta will reduce and it will become less than L by 250. So one way is to provide a camper. Now, in case where pre-stressing can't be done, what are the other things that we can do? We need to design the member again by enhancing the depth of this member so that we can increase the stiffness of the concrete and reduce the deflection. Or if there are constrained on the cross sectional dimensions of the reinforced concrete section, then we need to change the grade of the concrete. We need to increase the grade of concrete, or we can reduce the effective span or loading on the member. So either way, we need to decrease this deflection in the concrete by any means possible. One more way is by providing compression reinforcement, because when we provide compression reinforcement, my neutral axis depth shifts upward and it reduces the total deflection in the member, especially due to creep and shrinkage. Okay, so that is also one option. So there are different options that are available if this deflection limits exceeds. Now, it is not always possible to calculate all types of deflection and check against the length. Okay, so this calculation that we do, dead load plus live load deflection and long term deflection, it is not always possible to do such calculation. So what IS code says, the span to depth ratio of a reinforced concrete section can be satisfactory for controlling deflection as long as material for which the beam is made is elastic. Okay, so based on the span to depth ratio also we can have a judgment of what will be the deflection in a reinforced concrete beam. Okay, so the basic so this is the relationship that is given by code. The deflection per unit length of a reinforced concrete section is equal to k times the ratio of span to the depth of the section. Okay, now what is this factor k? So these are modification factors. Okay, so the basic value of span to depth ratio we can get from clause 23.2.1 of IS 456. So from part A, for different types of end condition, if my span is less than 10 meter, my L by D value will be equal to either 7 or 20 or 26. Okay, so basic value of span to effective depth ratio is this. Okay, now if the span to depth ratio that we have provided, okay, so this is the limit that code is saying should be there. If the L provided by D, if it is less than these values that are recommended by code, then we can say that the deflection will be under control. If the value that we have provided it is more than these limits, then we say that the deflection is not under control and we need to redesign the section. So this is how these values are important to us. Okay, however, we have assumed the section is elastic, but in reality, for a reinforced concrete, stiffness depends upon several factors, such as the percentage of steel that we have provided and the state of cracking. Therefore, this span to depth ratio needs to be modified from basic value, and that's why we have this factor K. Okay, and this K factor, it is a combination of different factors: Ks, Kt, Kc, and Kf. So this Ks is the modification factor for span length. Kt is the modification factor for tension reinforcement, Kc is the modification factor for compression reinforcement, and Kf is the modification factor for flange beam. Okay, so for span length, as per part B of clause 23.2.1, we can see if the span is above 10 meter, then the value, basic value, it needs to be modified by 10 upon span. Okay, so as the span increases, this basic value will continuously decrease by this factor. Okay, so this is my case factor. For KT and KC, there are different curves that has been given in the code. So this figure 4 is the modification factor for tension reinforcement. So based on the Fs value, which is 0.58 times Fy times ratio of steel that we have required and ratio of steel that we have provided. So based on the percentage tensile reinforcement and this Fs value, we can calculate the modification factor due to steel reinforcement, and based on the compression reinforcement percentage also we can calculate the modification factor. Okay, so figure 5 gives us the modification factor for compression reinforcement, figure 4 gives us the modification factor of tensile reinforcement, and figure 6 gives us the modification factor for depth of ratio of span to effective depth. Okay, ratio of web width to flange width for based on this. So BW by BF, the ratio of this again can give us the modification factor. Okay, so these are different modification factors that we incorporate in the basic value to get the effective L by D limit. Okay, now let's use this on the question that we have seen. So for the previous question, let's check whether the design is safe for total deflection under as per IS 456 guidelines or not. Okay, so how you will approach this? You know the total deflection. Okay, so we will check the total deflection with L by 250. And suppose if we don't know the total deflection, then we'll check the total deflection by calculating delta by L is equal to K times L by D. So this L K times L by D will calculate, and we'll check whether this K times L by D is actually less than the L by D that we have provided or not. Okay, actually what we have provided is less than this K times L by D or not. So both checks will do. Okay, just to check, just to see how we apply the concept of IS 456. Okay, So can anyone tell me the answer? Okay, total delta it was 25.067. So whether it is less than L by 250 or not, can you check? Okay, so total deflection that we calculated was equal to 25.067. Okay, and we want this to be less than L by 250. Okay, so L by 250 is nothing but 7,000 upon 250. 7,000 upon 250 is 28 mm. So total deflection that we had, it is less than this 28 mm. So we can say the design is safe right now. Now if we check in terms of L by D provided, so L by D that we have provided, it is equal to 7,000 upon 540, which is 12.96. And from IS code, what is the L by D limit that we have? So L by D limit is nothing but basic value times modification factor K. So since we have a simply supported beam, and so my basic value will be equal to 20. Now my span is 7 meter, which is less than 10 meters. So KS factor will be 1. KT, the percentage tensile reinforcement that I have provided, it is 1.212. Okay. So Fs is nothing but 0.58 times Fy, and whatever I have provided, it is equal to the design requirement. So 0.58 times 415 will give me 240.7. So for this 240.7, so it is for 240.7 is something here and 1.2 is somewhere here. So when you will calculate this modification factor, it will come out to be close to 1, close to this line 1. So we can say the modification factor due to tension reinforcement, it is close to 1. So I am taking as 0.95. Since there is no compression reinforcement, then Kc will be equal to 1. And since there is the flange width to web width is also equal to 1, so Kf will be also be equal to 1. Okay, so this basic value of LD, it will be just modified by one factor, which is 0.95 times 1 times 1. So it will be 20 into 0.95, which will be equal to 90. So this was the limit, and this we have provided. So since the provided L by D is less than the L by D limit, so we can say that the section is safe against total deflection. Okay, so in exam there can be question like this also, where you will be given the span of the beam and the effective depth of the beam, and you are given the codal provisions or charts. So from that you need to check whether the beam is safe or not. Okay, so like that also questions can come. Everyone clear with this approach? Everyone clear with the use of IS 456 for calculating the deflection? Any doubt in this part? Okay, so let's see about cracking now. Okay, so the second part of serviceability limit control is cracking in reinforced concrete. So when we talk about cracking in reinforced concrete, it can occur due to several reasons. There can be cracking due to direct tension. Okay, there can be cracking of a reinforced concrete beam under flexural loading in tension zone. There can be cracking in due to shear. So we have seen cracking, flexure plus shear cracking or diagonal cracking can occur. There can be cracking due to torsion on the surfaces. There can be cracking due to corrosion. There can be cracking at the bond between steel and concrete. There can be cracking while pouring the concrete if my slump is very high. So what can happen? This is my reinforcement. I am pouring the concrete. The concrete will just flow at the top, so we'll get a crack here also. This is also known as top bar effect. Okay, so there can be cracking like this. There can be map cracking due to shrinkage on the concrete surface. So cracking can occur due to several reasons. Now What IS code says, it is important to keep the crack width under control for proper functioning of a reinforced concrete. So as per clause 35.3.2, the maximum allowable crack widths are zero point 0.3 for mild exposure, zero point 0.2 for moderate exposure, and zero point 0.1 for severe exposure. And it is believed that if the crack is less than zero point 0.2 it will heal autogenously. Why? Because the moisture, it will go inside the crack, it will hydrate the unhydrated cement paste, and CO2, it will carbonate the portlandite. So there will be extra precipitation of CSH and CaCO3, which will seal the crack. Okay, if the crack is less than zero point 0.2 we say it will heal automatically. However, why we need to control the crack width? Because again, for appearance, if the crack is more than 0.25 to 0.35 then it doesn't appear good and it will be a concern for the public. If there is cracking, there can be problem of leakage, especially in liquid retaining structures like water tank. And if there is cracking in concrete, there can be problems of corrosion in the in the reinforced concrete section. So suppose I have a reinforced concrete section where reinforcement are present here. If there is no cracking, what will happen? The aggressive ions from the surrounding, it will ingress through the pores inside the concrete to reach the reinforcement surface. However, if there is already a crack in the concrete, the ions can freely move through the crack and reach the reinforcement surface, which can speed up the corrosion activity. So that's why, for that reason also, crack control is important. Now, cracking can be influenced by multiple factors: the tensile strength of steel bars, the thickness of concrete cover, the diameter and spacing of bar, the depth of the member, of the location of neutral axis, and the bond strength. So, there are different factors which can influence the crack width. Among these factors, the key factor which dictates the cracking in concrete, it is the mean tensile strain in the neighboring reinforcement. So, suppose we have reinforcements, so what is the strain in these reinforcement, that is important for crack width. Then the distance of a crack from nearest longitudinal bar, okay, that is important. So suppose this is my reinforced concrete section, okay, and I'm calculating the crack width at this point. So what is the distance of this point from the nearest longitudinal bar, which is represented by ACR? That is important for crack width calculation. And the distance to the neutral axis location is also important. So as we go farther away from neutral axis, we know the moment acting on the section increases, so the cracking potential will also increase. So that's why distance from the neutral axis is also important. And how we can control crack width? By limiting the tensile stress in steel. Okay, so if the stress in steel is low, the strain in steel will be low, so the cracking will be lower in concrete. By minimizing the spacing between the reinforcement, so if we will keep the reinforcement close to each other, then we can minimize the cracking. Or by providing bar as close to possible as concrete surface. Why? Because we don't consider concrete's tension capacity. Okay, the capacity of concrete to take tension load is very low. So if we'll keep the steel reinforcement very close to the concrete surface, so we can arrest the cracks very close to the surface, so cracks won't propagate deep until it reaches the steel surface. So that's why this point comes, providing bars as close as possible to the concrete surface in the tension zone. Okay. Now, how can we estimate crack at a particular point? So for that, we saw this crack width calculation in the discussion. So if we take different points on the concrete surface, we can calculate crack width as this formula: a constant times ACR times epsilon n. So this constant, it depends upon the type of rebar. If it is deformed bar, then the value is 0.3. If it is a plain bar, the value is 4. ACR is the distance of the point from the nearest rebar. Okay, and epsilon m is the average strain that is there in the steel at a considered level. Okay, so suppose epsilon m, so suppose strain in steel I know at this point, then what is the strain corresponding to this point? That is known as epsilon m. Okay, now, how to calculate the value of epsilon n? So, for this, code has given epsilon m is equal to epsilon n minus epsilon 2. So, epsilon 1 is the average steel strain at a considered travel of crack. Okay, so epsilon 1 we calculate from this relationship. Okay, so we considered the concrete as a cracked section. For that cracked section, we calculate FST. We know the ES, the modulus elasticity of steel, and we know the depth of the cracking point from the top. We know the depth of my rebars from the top, and we know the depth of neutral axis. So just like superimposing this depth d minus x to the strain at this level, we will change to strain at this a dash minus x level. Okay, so for changing that, we multiply this by a dash minus x upon d minus x. Okay, and for FST, we know it is my by I. So m is the moment that is acting on the section. Y is d minus x. Okay, for this y is total distance, this y. Okay, y is the distance from neutral axis, so it is d minus x. Okay, this distance, and I is the cracked moment of inertia that we can calculate. Okay, and epsilon 2, it is taken into consideration to take the effect of tension stiffening effect. So that is given by this relationship that was given in the, that is given in the code. Okay, so based on these two relationship, we get the value epsilon m. When we get, once we get the value of epsilon n, we can calculate the crack width. Okay, we know the point, how far it is located from the nearest reinforcement, so we can calculate the crack width, and then we can have a judgment which part is more critical to cracking in a reinforced concrete section. So generally, as this distance increases, the chances of cracking potential, it generally decreases. Okay, so that we'll see. Okay, so let's see the application quickly using this question. So we have a reinforced concrete beam. Okay, its dimension is given to us. We know the reinforcement, how much spacing is between the reinforcement and the clear cover, and there are 2 points at which I want to calculate the crack width. Okay, so can anyone tell me how you will approach this question? Simply just explain me the approach. So similar question we have seen in the session also. So I will just quickly tell you the solution if one, if anyone can tell me the approach. What is this plus minus Khushbu that you have written? So can you tell me how we'll approach this question? Okay, so approach will be, first I need to calculate the cracked moment of inertia. So the same way we talked in the deflection calculation, here again we'll calculate the cracked moment of inertia. Once we know the cracked moment of inertia, I will calculate the strain stress in steel. Okay, stress in steel. Once I know the stress in steel, I can calculate the value of epsilon 1 and epsilon 2 for both the locations. So a dash, it is x plus x by 2 for point B, and a dash is equal to the total depth d for point A. Okay, so using that we can do the calculation. Okay, so I will just quickly tell you the solution to this question. You can give it a try on your own, or you can just see how I am approaching here. Okay, so BD cube by 12, B is 300, D is 550. Okay, so when you will calculate the gross moment of inertia, it will come out to be 4.16 into 10 to the power 9. Then yt is d by 2, so that is 550 divided by 2, 275 mm. Modulus of rupture of concrete, it is zero point 0.7 under root of fck, so zero point 0.7 under root of 30, it will come out to be 3.834 mpa. Moment of inertia of cracked concrete, FCR times Ig upon Yt. So all three values we know. So moment of inertia of cracked concrete, bending moment of cracked concrete, it will come out to be 58 kilonewton meter. Actual moment which is acting, we can get from the loading condition. So we know the load which is acting, it is 20 kilonewton per meter. So 20 into 6 square by 8, 6 is my span of the beam, so you will get 90 kilonewton meter is my moment, which is more than the cracking moment. So that's why we are considering cracked section. Modulus of rupture, ratio of elasticity, ratio of moment modulus of elasticity, so that will come out to be 7.3. Then from transformed section, when you will calculate the depth of neutral axis, you will get the depth of neutral axis x will come out to be 130.25 mm. For this depth of neutral axis, you can calculate the cracked moment of inertia. So it will come out to be 1.162 into 10 to the power 9 mm to the power 4. Okay, so these are the basic calculation that we saw in the last question also. So that's why I've just quickly shown you the value. So this is the first initial approach that we need to opt. Okay. Now, once we know the cracked moment of inertia, I can calculate the stress in the compression, stress in the steel. So that is the moment which is acting on the steel, which is 90 into 10 to the power 6 times d minus x. So d minus x is 500 minus 130.25 divided by moment of inertia, that is 1.162 into 10 to the power 9. Okay, so when you will do this calculation, the stress in the steel, it will come out to be 28.64 MPa. Then epsilon Cs you can calculate from stress upon modulus of elasticity of steel, modulus of elasticity of concrete. So it will come out to be 0.00105. Okay, so this is epsilon Cs. Okay, strain in concrete at the steel level. Now to uh, convert the strain from steel level to actual crack level, we have point A and point B. So for point A is equal to D. So I will just convert this A as D 500. Okay, X is equal to 130.25, and D minus X we know it is 500. This capital D it will be here and small d is here 130.25. So epsilon 1 at point A, it is 0.00119. At point B, A is nothing but x plus x by 2. So x plus x by 2 minus x will be equal to zero point 0.5x. So I can write here as 0.5x. So zero point 0.5 times 130.25 divided by 500 minus 130.25. So this will come out to be epsilon 1 at point B will come out to be 0.00018. Similarly, for epsilon 2, you will use this relationship that is given in the question. So everything else will remain the same, just the value of A is changing. Okay, so for point A, the value of A is equal to D, and for point B, the value of A is equal to 1.5 times X. Okay, so when you will substitute all the values, you will get E2 value at point A, it will be equal to 0.000025, and E2 value at point B, it will be equal to zero point 0.4 times 0.4. Okay, so E1 and E2 we know. So E1 minus E2 will give me the strain at the considered level, and so WCR we can calculate as 3.3 will be the factor since we have deformed rebars. E2 minus E1. So at point 8, E1 is 0.00119, A2 is 0.00025 times ACR. So ACR is the clear cover. Okay, at point A, this point is located nearest to this rebar, and this distance is 40 mm that is given to us in the question. Okay, so ACR I can substitute as 40. So it will come out to be 0.124 mm. So the crack at this location, it will be of width of 0.124 mm. Now for point B, what will be the nearest distance? So this distance I need to calculate from Pythagoras theorem. Okay, so this I know, this total distance I know it is 100 mm. This is 100. Okay, this is 100, and total width is 300. So this distance will be 50 mm. Okay, now this we know it is equal to 1.5 times x, and this is d. So this distance will be d minus 1.5 times x. So we know this, so we can calculate this. Okay, and ACR will be, suppose this distance is coming out to be as b. Okay, so ACR will be B minus diameter of this radius of this rebar, which is equal to 10. Okay, so this is how we calculate the ACR value. So 50 square plus d minus 1.5 x square whole under root will give me the value of b. So this value of b, it will come out to be 308.7, and 308.7 minus 10 will give me the ACR value, so it will come out to be 298.7. So this is my distance of this point from nearest longitudinal rebar. So when you will substitute this value here, so ACR, it will come out to be 298.7 mm. So WCR, it will be 3.3 times 0.00018 minus 0.4 times 04 into 298.7. So this will come out to be 0.138 mm. Okay, so at point A and point B, this is how we can calculate the crack width. And since at both the points the crack width is less than 0.2 mm, then we can say these crack will be autogeneous. They will heal automatically. They are not an issue, much of an issue to the structure. Okay, so this is how we approach the question. Everyone clear with this approach? Any doubt in this crack width calculation part? Okay. Okay, so let's see ahead now. Okay, so the last segment was about bond strength between steel and concrete. So if you remember, when we talk about, I guess there's some doubt. Yes, Satish, you can ask.
So there is a question in assignment regarding the crack bit. So there is question number 9. But there is
Which
it has
assignment? Assignment 10, 11, which assignment?
sir 11.
Okay,
So question number 9. So it has not been mentioned that where the crack width has to be calculated. Like point has not been mentioned.
just let me check the question once.
Question number 9 of 11.
Can you just paste the question in the chat box?
Yes, sir.
Okay, let me read. A beam, we know the grade, we know the steel grade as with the tensile capacity. Using the crack width formulation, spacing between the bar cover is given. Okay, and EM we have set to assume as 0.001, as compute the approximate crack width, choose the closest value. Yes, there is some problem in this question. They should mention at which location the crack width needs to be calculated. Okay, you can just drop a message to the NPTEL team in that discussion forum on the portal that we have now. In that portal, just post this query. The team will respond and they will correct the question.
Okay, sir. Okay, sir.
Okay. But I hope the concept is clear. Okay, there are three things that we require for calculating crack width. One is the constant value that will depend upon the type of steel. If it is plain steel, we take it as 4. If it is deformed steel, we take it as 3.3. Then epsilon m value. So in this case, it was given to us directly as 0.001. If it is not given, then we need to calculate epsilon 2 minus epsilon 1, that we need to do. Okay, and then the location. So generally, I think in exam this epsilon n will be given directly to you, because this calculation can be tedious. You need to calculate the cracked moment of inertia, then you need to calculate epsilon 1, epsilon 2. There is a complete formula that you need to remember. So I guess in exam epsilon n may be given to you directly in the question. But this ACR value, that is something tricky. Okay, it depends upon the location, and in that also it is not just directly using the Pythagoras theorem. You need to subtract the radius of the rebar, because you're talking the location of crack from the surface of reinforcement, not from the center of reinforcement. So that is very important to be taken care. Okay. So the last segment that was there in the session was about bond between steel and concrete. So if you remember, when we were talking about design of reinforced concrete beam, we assumed that we take an assumption that the plane section remains plane after bending. Now, for this assumption to be true, we assume that for a plane section to remain plane, the strain in the embedded steel reinforcement is assumed to be the same as the strain in the surrounding concrete. So suppose this is my concrete, these are my reinforcement. So at this level, whatever strain is there in concrete, it is the same as the strain which is there in the steel that we assume. However, for this to be true, it is essential that the bond between the steel and the concrete is sufficient enough so that the strain transfer is uniform. Okay. However, if this bond is not strong enough, then what will happen? The strain in steel will be different, the strain in concrete will be different. So, this assumption that we make while designing it won't be correct. So, while doing all this calculation, while making the strain diagram, and while calculating this epsilon cs, epsilon s, all this will nullify if this bond between steel and concrete is not perfect. Okay. Now, what all things that contribute to the bond between steel and concrete? So, first is the weak chemical adhesion. So, we know in concrete there is precipitation of hydration products. So, these hydration products, they create a gum-like property to the steel reinforcement that gives a chemical adhesion between concrete and steel. Then there is mechanical friction between steel and concrete. Concrete is a rough material compared to steel, so that can generate some friction between them. Then there's slip induced interlocking between steel and concrete. So generally the steel surface has rough nature. So when the steel is moving, suppose due to some load, the steel is forcing out of concrete, then due to this rough texture of steel also there will be some bonding between steel and concrete. And finally the one of the major factor is the deformed bar. So when we are talking about deformed bar, the surface is like this, there are ribs on the surface. In between the ribs there is concrete that interlocks between the steel and the cover. So this interlocking of concrete and steel together, it gives us the force, the bond strength between steel and concrete. Okay, due to the this projections which are known as ribs. Okay, so these are four primary sources of bond strength when we talk about the steel concrete interface. Okay, now if we consider a reinforced concrete beam under the action of load, and we consider a small segment dx, okay, in this beam. So in this dx element, we know that the compression force at the above neutral axis and tension force below neutral axis, it will vary. Okay, so at section a, which is nearer to the support, the moment is m. At section b, which is more nearer to the mid part, it has a greater moment, m plus dm. So here the force will be c, the force here will be c plus dc. Similarly, the tension force on the rebar here will be t, and here the tension force will be t plus dt. Now this additional dt force, it will generate a kind of pull on the rebar. If I just talk about this small section, to resist this pull, there is bond stress that has developed between steel and concrete, which will try to resist this additional force dt. So we can write dt as dm upon j by dt, j times d. So we know what is m. M is nothing but force times the lever arm distance. Okay, so that lever arm distance we can write as j times d. Okay, so this d additional dt force we can write as dm upon j times d. Okay, so if we know the value of this unit force that is acting on the rebar, then how much resistance it provided by the bond, that will be equal to the total perimeter of the rebar. Okay, I have shown here one rebar, there can be multiple rebar that is present at this location. So summation of perimeter of all the rebars times the units bond stress between rebar and concrete times this total length, which is dx for this element. Okay, so that will be equal to dt. So this u value you can calculate from this. Okay, so average bond strength, it is the bond force that is acting between the steel and concrete, it should be enough to uh, nullify this effect of additional dt force that is acting. If it is not able to nullify this dt force, then there will be no perfect bond between steel and concrete, so all that strain distribution that we talk about, it won't be correct. Okay. Now, while calculating, we assume that this force U is uniformly there on the rebar. However, in reality, it is not true. Okay, so where the cracking is there, the strain will be more in the steel. Where there is no cracking, the strain will be lower. Similarly, where there is cracking, the strain in concrete will be zero. However, where there is no crack, there will be some stress there present in the concrete also. So this, sorry, not strain, stress. Okay, so this stress distribution is not uniform along the length of the rebar. Okay, it can vary. So the bond force that is acting along the length of the rebar, it can also vary. So just near the crack, the bond force will be maximum, and at the position of crack, the bond force will be minimum. Okay, so that is how the bond stress can vary. It is not a uniform thing that is acting all over the surface. And when we talk about this deformed bar where ribs are present, the pull force that is acting on the rebar, it is generating some downward effect on the ribs, and this will generate some outward effect on the concrete. Okay, so that's why just near the ribs there is maximum bonding, and as we move away from the rebar, the bond strength decreases continuously because of this force element which is resisting the pull. Okay, however, if there is no sufficient bonding between steel and concrete, then what will happen? So initially, as the force will increase, what will happen? This adhesive bond and friction will give up, and concrete will start to crush locally at the location of bond. And as soon as the load will increase further, what will happen? This rebar will try to come out. Okay, and it will split the concrete either horizontally, like vertically like this, or horizontally like this. So the type in which, the way in which this cracking occur, it depends upon the distance between the reinforcement and the cover. Okay, cover property. So this is the problem for us. So how we ensure that this splitting doesn't happen, slipping doesn't happen, and this perfect bond that is developed between steel and concrete? So for this, we have a concept of development length. So what this development length tells us? So development length in the reinforced concrete, it refers to the minimum length of reinforcement required to be embedded in the concrete, so that we can ensure that there is enough tensile strength that has developed at the interface without slipping. So we want that this reinforcement, it should not slip out of my concrete. Okay, there should be enough bonding there should be enough bonding developed between the steel and the concrete before this uh, failure to occur. Before failure, slip should not occur. Okay, so for that we need to embed this reinforcement enough inside the concrete so that enough bond strength has been developed, and this embedment length is known as the development length. Okay, so if you see in the figure here, so the embedded rebar in concrete, it is subjected to some tension force T here. Okay. Now generally this stress on the interface, it is parabolic in nature, but just for simplification we assume it is uniformly distributed. Okay, so when a bar is stressed in tension, the bond between steel and concrete, it tends to resist this slip of the bar. Okay, and this development length ensures that sufficient bond is developed between steel and concrete so that stress can be transferred from steel to concrete effectively before slipping. So we want slipping not to occur. Slipping should not occur. Okay, there should be sufficient strength that has been that should be developed at the interface. Okay, that is the concept of development length. Okay, so if we consider this pull force acting is T, okay, so what code says, to fully develop the bond strength between the steel and concrete, the total surface area, that is 2 pi r times length times the average bond stress at steel concrete interface, it should be equal to this force that has been developed. Okay, so force will be nothing but the area of bar, that is pi d square by 4, times the force, that is a stress acting in the steel. Okay, so from this we can calculate this embedded length that we need, and that embedded length is known as development length, which is given by this formula. Here tau bd is the bond strength between steel and concrete, which depends upon the grade of concrete as well as the type of steel. So if it is a deformed bar, we increase it by 60%, and if the bar is present in the compression side, we increase it by further 25%. Okay, so based on this we can calculate the development length. Now, suppose I have a reinforced concrete section like this, okay, which is experiencing some pull from here, and I have provided a development length LD, but LD is not enough. Okay, now what we can do, we can't increase this rebar length further. So what code says, there are multiple things can be done. Either we can bundle the bar. Okay, so if we place multiple bars in bundle, then we can increase the development length, or we can use you can use anchorage or bending. So instead of increasing the bar directly from here, we can provide some bending and anchorage to increase the bond strength. So this will effectively increase the development length, which will increase the capacity of the rebar to take the tensile force T acting on it. Okay, so as per clause 26.2.1, when bars are bundled in contact, the development length of each bar shall be equal to the individual bar, increased by 10% for 2 bars, 20% for 3 bars, and for 33% for 4 bars in contact. And as per clause 26.2.2, the bars are provided with anchorage and bends or hooks. So deformed bars may be used without anchorage provided LD requirement is satisfied. However, if LD requirement is not satisfied, we provide anchorage and hook. So if we are providing an anchorage of 90-degree, the equivalent length we can take it as 85, and this is the additional length that we have provided here. So total length, it will increase by, suppose if this was LD, now my final length will be LD plus 45 plus 85. Okay, so that is how we can increase the development length. Instead of 90-degree, we can provide a 180-degree curvature also, bend also, and we can calculate the development length. Okay, so such cases we do when my section has a limited dimension and enough bond strength has not been developed between steel and concrete. So that's for those cases we provide bends and hooks. Okay, so just based on this concept of development length, try to answer these three simple questions. And in the meantime, if you have any doubt in this part regarding bond strength between steel and concrete, why it is important and why we are talking about development length, you can ask. Okay, what will be the answer for first question? Development length ensures. What is development length ensuring to us?
हाँ
B, sir.
अच्छा अच्छा
The full
ठीक है
stress is developed between steel without slips. So that is the concept of development length. We don't want the rebar to slip before actual failure of interface. And development length ensures that whatever stress is acting on the steel, it is thoroughly developed at the interface. So steel is able to completely transfer the stress from steel to concrete before slipping. So that's why we provide development length. Development length in compression compared to tension is generally lower or higher. So suppose we have a reinforced concrete section and there is compression reinforcement also, there is tension reinforcement also. For tension reinforcement, and both the rebars are subjected to a similar pull force of T. Okay, so which rebar will have a higher development length and which rebar will have a lower development length? Why A? Yes, A is the correct answer. Because when we talk about rebars that are present in compression, their bond stress is higher. So this u value that we saw here, this u value is higher when the rebar is present in the compression side rather than the rebar in tension side. Why? Because in tension the concrete is also experiencing tension, so that decreases the if low bond stress at steel and concrete interface. However, when this rebar is present in compression, both concrete and steel are experiencing the compression effect, and that's why this u value it is more in compression side compared to tension side. So if this u value is more, what will happen? If this u value is more, then this development length requirement it will decrease. Okay, so that's why you say development length in compression is generally lower compared to tension. If we have if concrete cover is poor and confinement is low, then which will be the correct? Will I require more development length or less development length? Can anyone tell me?
More.
Why more?
B.
Because if the cover is poor, then that means that the concrete grade is lower, and we have seen in this chart, you can see if the concrete grade reduces, the bond stress between the steel and the concrete also decreases. So if this tau bd will decrease, the ld will increase, so more development length will be required. Okay, now just give a try on this question. We have a simply supported beam and it is subjected to a bending moment. We know the grade of concrete, we know the dimension of steel rebar and the grade of steel rebar, and we know how much development length we have provided. It is 400 mm. So is this development length enough for this section? How we will check such things? Can anyone just quickly tell me? Okay, so such question can come in exam also, which can be very confusing to you at first. So first of all, we know the moment that is acting on the beam. Okay, and so for this moment, we first need to check whether the rebars are completely stressed or not. If the rebars are not completely stressed, then the development length will be different. Okay, so this factor that you see here, Fs, it is the stress in the steel. So stress in steel will depend upon how much movement is acting. If this movement acting on the beam it is equal to balanced limiting moment, then we say the stress that is developed it is complete. If the stress the moment acting on the beam is less than limiting moment, then the stress that is acting on the steel will be also be lower. So this Fs value will depend upon how much stress is actually acting on the beam. Okay, so that's why first step is to check whether the bar is fully stressed or not. Okay, for Fs value. Okay, so how we can check this? By calculating the limiting moment. Okay, so we know the property, we know the b is equal to 300. We know effective depth d. Okay, and we know the grade of concrete and grade of steel. So mu limiting we can calculate directly from the design charts. So we know mu limiting divided by fck bd square for 500 grade steel, it is equal to 0.133. So from this, if you calculate mu limiting, it will come out to be equal to 299.25 kilonewton meter. And what is the moment that is actually acting on the beam? It is 300 kilonewton meter. So we can say the moment which is acting, it is very close to mu limiting. So if this is true, then F is, we can write it is equal to 0.87 times Fy. So we can assume that steel is fully stressed. Okay, so if you Fs is 0.87 Fy. Okay, so we can calculate how much development length is required. So that will be nothing but using this formula, 5 times Fs upon 4 tau bd. So 5 is 20 times 0.87 Fy divided by 4 times tau bd. The grade of concrete that we have used is M30. So M30 will correspond to 1.5. And since we are using deformed rebars, okay, so here I should have provided this, these are deformed rebars, okay, so I will increase this by 60%, so 1.5 into 1.6 I need to do. So total development length that was required to resist the tension force on steel, it is 906.25. However, the one that we provided, it is 400 only, so that is not enough. Okay, I need to increase the development length. So how I can increase? I will provide anchorage and bend. Okay, so how we design for such thing? So I will assume I am providing 180-degree bend. Okay, so when I provide 180-degree bend, the development length, it increases by 16 times diameter, so 16 times 20 is 320. So additional anchorage that is required, so that extension. Okay, so if you see here, I will just draw a diagram. Okay, this right now it is 400 mm, and this is what I am designing for. Now this part, it is 320 mm development length. Now what is this that that I need? Okay, this is unknown for me. Okay, so I can calculate this. So just by total requirement, so extension I can calculate as what is the total requirement, 906.25, 400 is also already there, and 320 came from an 180-degree bend. So that will come out to be 186.25 mm. So this extension I need to provide is 186.25. So in this way, if the development length that we have provided is not enough, we can design for anchorage and bend also. But for this, first is to calculate whether the stress bar is fully stressed or not. For that, you need to know the limiting moment of inertia, limiting bending moment, and based on that, you need to check how much stress is there in the steel. Okay, so such simple questions can also appear in exam. Okay, that you need to take care for. You may directly calculate this LD value assuming this the steel is completely stressed, and you may report an answer, but in reality the steel was not completely stressed. So you need to have this check first before you approach the question. Okay, everyone clear with this question? Any doubt in the session today? So this was all for today's session. We talked about serviceability, we talked about deflection, short term and long term deflection. We talked about IS provisions on deflection and effective length to depth ratio concept. We talked about cracking, how we can calculate the crack width at a particular point, and we talked about bond between steel and concrete and the concept of development length, and how we can provide anchorage and hooks in the to the reinforcement if development length is not enough. Okay, so this was everything for today.